How do you do, ladies and gentlemen, and boys and girls, and teachers? I'm Julius Sumner Miller, and physics is my business. And as on every program, on every lesson, some very special business, properties and effects of electric currents. The effects are staggering in their meaning for humankind. Consider the following. I have here a heavy conductor, and just below it, a compass needle, and I'm going to align them both so that the needle is in the plane of the wire frame. Now I am going to give rise to a current in that horizontal wire by connecting to a storage battery. I'll connect first this terminal, and then momentarily to the other. And you will observe a marvelous thing, that when there is a current in this conductor, a magnetic field arises, and magnetic fields interact with magnetic fields, so we would hope the needle suffers a deflection. Watch it now. Watch. There it is. And the deflection was such as to make this end of the needle come toward me. Watch it again. There it is. If now I should change the direction of the electric current by changing the polarity of my connections here, watch it now. Watch it. This end of the needle should move away from me. Watch. I'm having a little trouble. Notice a little trouble to make the connection. There it is. And so we have discovered the magnetic effects of electric currents, first observed in 1820 by the Dane whose name was Ørsted. O-E-R-S-T-E-D. Hans Christian Ørsted, 1820. Accidentally observed the deflection of a magnetic needle, a compass needle, in the region of a current-bearing conductor. Now that is historic, because when Michael Faraday heard that Ørsted had observed the magnetic properties of an electric current, namely that electricity produces magnetism, Faraday wrote in his notebook, "Make magnetism produce electricity." See the converse of it. And it was 11 years, 1831, before Faraday accomplished it. As he wrote to a friend, "I have been fishing lately, and it may be only a weed that I pull up. But the weed, which came to be called electromagnetic induction, has lighted the world." Indeed, when he discovered it, he showed it to the Prime Minister. And what did the Prime Minister say? "Mr. Faraday, of what use is this?" Whereupon Faraday answered it in a classical way. Let's see, yes. "Mr. Minister, one day you may be able to tax it." Wonderful commentary. So, electric currents produce magnetic fields. Another wonderful effect of an electric current. I have here two lead plates connected to a framework, and here in this vessel, some copper sulfate. I'm going to put the two lead plates, which for all purposes here look alike, in here, and connect the lead plates to a source of electric energy, a storage battery. And what will happen? The copper sulfate is an electrolyte, a good conductor, because there are ions available. I'm having trouble here. That's okay. And we should discover some dissociation of the copper sulfate, and I hope to show you that copper will be deposited on one of the plates. So I am copper plating. Here we have the conduction of electrolytes, an effect of electric currents. Here's another one, the heating effect of electric currents. I have here a framework. I want to be sure that I am not connected yet. Yes, there's the plug. Here is a framework, two pointed shafts on which I have lodged a frankfurter. So, just like that, the pointed shafts emerge here. I have the two metal rods connected to an electric lead, which I can now energize from the house line. And I say that this frankfurter will be cooked. Why? Because the meat and the stuff, the salt in solution in the meat product, is a good electrolyte and hence a good electrical conductor. And if we watch closely at the electrodes, we will see some oozing, some steam, some heat generated. Watch it now. I'll just let that go, and I'm going to get down there closely. Yeah, I see it. I see it. I see some cooking there. There it is, and you catch it on the monitor. So I am cooking a hot dog in this manner. Let me show you another wonderful effect of an electric current. Here is a copper wire and a dry cell. A dry cell. Now, if I short circuit this dry cell by connecting terminal to terminal, I have a heavy current in the wire. I'm going to put some iron filings down here, and you will see that the wire unconnected has no effect whatsoever on the filings. But now let me give rise to a current in this. Now watch. Do you see the filings connected there? There they are. Now, I don't want you to think that I have made a magnet out of that wire. No, no. There is a magnetic field associated with the current in the wire. Let's look at my hot dog. Oh, yes, there it is. Let's get it close again. There, the juice is oozing, and pretty soon I'll eat it, which is what should be done with a hot dog, which is a hot dog. Another effect of electric currents. I have here a coil of wire. This demonstration is virtual. I do not do it for a reason which you will see in a moment. Now, what would I ordinarily have? In this lower vessel, I would have some mercury. The lower end of this coil of wire would just make contact with the surface of the mercury. I would connect this coil of wire, its upper end and its lower end, to a source of electric energy such as a battery. What would happen? We would have a current in the coil, and because each conductor or each loop bearing current gives rise to a magnetic field, there is some mutual interaction between the adjacent loops, whereupon the coil would do this. It would be pushed together because of a weakening of the field between adjacent loops. Now, when it does that, the lower end of the circuit would be broken, the current would cease, and it would fall back again, make contact again, and this is what the coil would be doing if I were to do the experiment for real. But now, why don't I do that? I don't do that for this reason. At every sparking and arcing at the mercury surface, some mercury is vaporized, and mercury vapor is very dangerous, exceedingly insidious and dangerous, and should be avoided. Let me take a look at our electroplating. Watch it. Here I am. Ho-ho, look at that. Isn't that wonderful? Look at that deposit of copper on this plate. A beautiful deposit of copper. Now there is some other stuff on the other plate, and I leave it as an exercise. What is the stuff on the other plate? Could I not have had, instead of a copper sulfate solution, could I have not had a silver solution of some sort, and a silver and a steel spoon that I want a silver plate? I could do that. I want to show you now, further, some wonderful magnetic properties of an electric current. I have here a coil of wire, of very few turns, heavy wire. Now, heavy wire, very few turns, means very low ohmic resistance. If I connect the ends of that coil to a storage battery, 6 volts, the battery highly charged, the internal resistance of the battery is very low. So I would have an enormously high current in the coil. Now, the coil, when energized, behaves like a magnet because it gives rise to a magnetic field. And if I have a rod placed so, and I connect to a battery, a wonderful thing happens. And I call this my electromagnetic gun, because when I close the circuit, the projectile will be pulled in. If I open it, it will be thrust out, and I better move this in case we have some disaster. Oh, wait just a minute. I have to get out and see my hot dog. Yeah, watch it, my hot dog. I am disconnecting the electric circuit. I want to get on the hot dog now. I am disconnecting the electric circuit, and if you give me your attention, I will show you how wonderful this is. Mm-hmm. Wonderful. My electromagnetic gun. Watch it. Watch the iron rod, the iron core. Watch it. Now, what happened? I did not open the circuit. Therefore, the rod did not emerge, but was pulled back for a reason you'll have to explore. Now I'm going to open the circuit at a critical moment. Watch it now. Uh-oh. Oh, notice, that gun backfired. I opened the circuit at the wrong time. I'll try it now. There we are. I'm going to do it again. Oh, do you see? It's very critical. Oh, there, it backfired, which means this is a very dangerous gun. It can shoot the shooter. I'll try it once more. Ah, there we are. And would you believe it? I have made such a gun which can shoot such an iron bar about 30 feet. Now, if you pointed that, do you see you could have a silent weapon? Shot silently, travel silently. More on the heating effect of an electric current. I have here a length of copper wire. Here a fully charged storage battery. Let me short the battery by putting across its terminals, such a copper wire. Watch the wire. Watch it. There it is. Melted copper. I'll do it once more because this is very dramatic. Let me tell you further. It is a very unhappy thing for the storage battery, too. But then again, anything in the name of science, as you know. Watch it. There it is. The heating effect of an electric current. Now, regarding the magnetic effects of electric currents, astonishing. Here is a heavy metal bar, and here another heavy metal bar. And what could I show with this? Let me give rise to a current in this bar, and let me give rise to a current in that bar. Depending upon the direction of the currents, either the same way or in opposite directions, the bars would either be pushed apart or pushed together. And this is very significant for transmission lines, because, as you know, if we have two transmission cables that are too close upon each other, the mutual interaction due to the magnetic fields is likely to bring them together and short them out. So we must have regard for those matters. Are you not agreed that the properties of electric currents are enchanting to contemplate? And I thank you for watching.